Hello, Mr. Aaron, Mr. Ryan. How are you today? Okay, so today we're going through some basic concepts of this hashing. Yeah, hashing, hash table. Yeah, hashing, hash tables. You know, hash tables. How do you define a hash table in Python? What's the alternative of hash table? Like we have been using that for a long time. You know, when solving some problems, hashing table. Like what? Any idea? What's that? If you want to look up the items in thingy, what do we call it?
Notebook.
Notebook. Yeah, notebook is the name that I give you. You know, but it's not official. The official name is hash table. Okay. Yeah. But why we call it notebook? Yeah, because you want to look up the items. You put the item in. You write a sentence in the notebook. You look it up. It's constant time. It's very fast. You don't actually need to perform the searches, right? So in Python we have this dictionary, yeah, dictionary. So we can declare a dictionary like that. A equal, this is a dictionary, yeah. A equals dictionary. You can do this dictionary, yeah, dictionary. Or the one way. First way is or you use this, yeah. Second, yeah, this is the what do you call it? Curly braces. And the third way is to what? A equals default dictionary, yeah, default dictionary. Okay, and then you can give a basic type of integer. This is the value type. That's the value. What type of a value? Yeah, type of values. These two, the same. These two just the same. So what's the difference between this and this? The difference is that when the key does not exist in the hash table, using this definition, if the key isn't in the hash table, and then you will return the default value for the type. For example, the int it will be the 0. Yeah, the default type of integer is 0. So look, if I can say look a something like a Eric. Okay, if I want to print the a Eric without ever putting the values of Eric, right? So that will give me the 0 unless I do a Eric equals 9 or whatever. Right? If I use the third approach, the default one. But if I use the first or second approach to declare the hash table, then a array will throw an error. Yeah, it will throw an error saying the key does not exist. The array does not exist in the table. That's the difference. But using these two, you know, you can always use this a dot get. Yeah, get array. And then the second value will be the default, which I can give like a 5. And then if Eric is the key is not in the table, then you will return the 5. If it's in the table, then you will look up the values for the key equals Eric, right? That's the dictionary. So what's the term complexity of all these? Like a lookup. I want to look up a key if a key is in a dictionary. What's the time complexity? There are a few operations, right? The second one is I want to update the key value pair, right? Update value with key, with the key, right? And the third one I want to delete the key, right? Basically, these are the three approaches, common approaches that are required for the hash table, right? Like a notebook. If I want to look it up a key, if it's Eric, if it's in a book, right? A key value, O1 constant, right? And I want to update like Eric, map Eric equals 9, right? And I want to remove it. What's the time complexity for all these three approaches? Come on. Anybody write it? O1. We want the fast terms. That's why O1, yeah. That's the obvious reason that we want to use this kind of data structure, because we want to achieve the O1 constant, right? O1 constant. So so we are talking about the hashing function. Yeah, hashing function. What's a hash function? Is the function that to map arbitrary length of data input into a fixed size table. Okay, fixed size. So what does it mean? So look, if I have a hashing table, like maybe there are only 10 elements, right? Only 10 elements. Maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yeah? 10 elements. This is a hash table with size 10. Right? And I want to put a key, any key, yeah? Any key. I want to put maybe 10 items, any items. For example, like something, Eric. I want to put this Eric thingy, yeah? And then there's a hash function, data. And then you give me, when this data is fit into this hash function, and it will give me a location to store this Eric data. So for example, it will store here. Right? And then another one, Ryan, and then go through this hash function, hash function Ryan. And then you will give me a key. Okay, maybe store here, right? Yeah. Okay, so the next time I want to look it up this data, Eric, Ryan, and I need to call this hash function again, and it will tell me where to look it for it. But this is done internally to look it up, to locate the locations, right? So if these keys, I mean, if there are many data, what happens? Can you imagine? Like, what happens if this table is 10, and then if I have like 100, a million data? What can you imagine? What can you imagine in this case? So if I have too many data here, and I want to map it into a fixed size, what happens? They are arbitrary.
It will take for a long time.
It will take for a long time, and this is not the most important reason. The another reason is there will be what? Collision. You know, the collision. Collision. What does it mean? Collision in English. Collide each other. It means the different input. For example, Eric and Ryan, they are different. These keys are different, right?
Mm-hmm.
But after the HD calculation, they might point to the same place, right? So one approach to solve this problem is to what? We can have, instead of solving one item, we can do what? We can point it a linked list or list, right? For each key, each hash key here, right? And for example, Eric is here. I store here, and Ryan, if the hashing function points to this location, and this location, yeah, and I can append it to the linked list, Ryan. So I don't overwrite. I don't lose the data. This is one way of doing it, right? One way of doing it. So we want to reduce the chance of collision. Right? One way of doing it is by picking up a good hashing function. Yeah, a hashing function. So this hashing function, hash data, it needs to do what? It needs to calculate the key, the values, the location, which is maybe a 32-byte integer, right? A location, or yeah, let's say if it's a 32-bit integer. No matter how big is this data, maybe a million, you always return a fixed size location, right? So we want this function to be, first of all, it has to be very fast, right? This function calculation needs to be fast. If it's slow, then there will be an overhead. Because this hashing function, I need to use it every time to do what? I need to use it every time to calculate the location when I want to retrieve an element from the table, when I want to update it, right? Or I want to remove it. These are three approaches, yeah? Three operations. What? Look up, update, yeah? For the hash table, update, remove, right? Remove. These are three things. These three operations all require me to calculate the hashing key, right? The key, right? So it needs to be fast. If it's slow, then everything will be slow. The second, I want to reduce the collection. Reduce the collection. What does it mean? Right? If you give me the Eric, yeah, or you give me the Ryan, I don't want them to point it to the same location, right? Because the same location, all these will be falling back into the linear search, right? Look, if these everything, just imagine in the worst case, if I HD always return 0. No matter what data you give, you want to put in the hash table, you all put it in the 0 location. Put it here, right? This is index 0. Yeah, if I put Eric, it is here. I put another Ryan is here. And mommy, daddy, right? Everything you put in here. So this hash function is not working. You always return a 0. Means that location is here. So what happened? Next time I want to look at do this. This becomes what's the time complexity if xt is 0? What's the time complexity? Oh what? What's the operation of looking up a key in the list? How do you find an element in the list?
You start from
The beginning
Yeah.
and then search it. What's the time complexity for that?
And
Oh well, yeah. Update. Update is based on lookup, yeah. First of all, you need to find it and then you update, right? Yeah. So update and lookup are the same. It's O(n). Remove. Again, if you want to remove it, you first need to find out where if it's in a table, right?
Yeah.
So it's still O(n), right?
Yeah.
It's not to mention that if you want to remove an element from the list, like maybe another O(n) to shift all the elements, right? We'll talk about that. So we want to reduce the collision. If everything is if Eric is here, store here, Ryan store here, mommy store here, daddy store here, great, because they're all in separate places. They have not collected each other. So this O hashing function helps us to retrieve this O(n) constant time, because the hashing function just points to the location which doesn't have other values stored, right? So I can just look it up, do whatever I want. Okay. And the third one is we call it avalanche effect. Avalanche effect. What does it even mean? What does this mean?
it's in winter.
So can you explain to me what's an avalanche effect?
So some people like to go skiing on mountain and then and if they don't escape, they'll be buried.
Okay, so yeah,
No.
Eric, what?
So technically snow falls down and then it does a big collapsing. This looks like a big cloud.
Yeah. So in this is what it means, but in computer in hashing effect is what? If I want to put this H Eric, yeah. Eric, if this tells me is I want to store this location at 100, right? And how about H if I have uppercase, okay, instead of lowercase? This needs to be even the key change slightly. What I mean by slightly could be very slight variations from lowercase to uppercase or vice versa. Right? You know what I'm saying? And then this value needs to be changed as well. It can be changed to maybe 0 or 2000, yeah? Do you understand? But if I change slightly, it give me 101 or 99. This is not good. So all I want, this is avalanche effect, which is good. It means that even a slight change in the key, this hashing function needs to give me something totally different. Do you understand?
Like 2000.
Yeah. Do you get it? This, yeah?
0.
Yeah. Let's call avalanche effect. It's good in the hashing table. These are the three. How do we measure if a hashing key is good? We want the hashing table to be fast. We want it to be less collection. We want it to be having this avalanche effect, right? So, okay. So another thing I want to mention here is that how do we mentioned about the list here. How do we remove a list, an element from the list? For example, like, okay, this is a list here. 1, 2, 3, 4, 5. I want to remove the element 3. How do we remove it? For example, these are the key, all the hashing table, hash, whatever, right? Points to a linked list, remember here, yeah? We talk about here. This is hashing table, okay, points to here. Hashing table, whatever they are, points to here, this location. And this is the linked list, right? So now I want to remove these 3, yeah? And I go through this list. Okay, I found the 3 here. I want to remove it. Alright, yeah, I want to remove these 3. So how do we do it?
Delete it.
Yeah, but how do we delete it? We delete it. How do we delete it?
Just delete it.
Yeah, okay.
Skip it.
Skip it, but we want to remove it, yeah?
Yeah.
One way of doing is this. I want to.
I know. Well, I know.
Yeah.
Okay, so you make you make one of these notes three the same thing.
Yeah, exactly. So look, I can copy this value to the last one. I don't care about the order. I put it 5 and then remove it. Yeah, got it? Why is that? Because look at the list. Yeah, remember the list. A equals list. Right? This is list. What's the time complexity of this one? What's the difference between this one? What's the difference between these two? Can somebody tell me?
A dot pop is from the right and A.
Okay, so like 1, 2, 3, 4. Okay, so can you tell me A to pop? What happened?
We pop the
Which one?
first one. No, yeah, the last one.
The last one. Okay. And A to pop 0.
You pop the first one.
First one. What's the time complexity between these two? Removing the last one is 1. Yeah, we just remove it because in the last we just remove it. But pop 0, what's the time complexity?
Owen.
Owen, yes, Owen. Why is that? Because computer needs to shift it, all the elements. Yeah? All the elements. So take it out, it needs to shift it. Look, 2, 5, 4, yeah, whatever. This is one way of doing it. Another way, some computers, the computer algorithms, sometimes they want to allocate another place and copy over. Right? This is ON as well. But generally speaking, a popping, we're talking about this, yeah? We are not talking about the double NDQ, yeah? Double NDQ is totally different. It's all, double NDQ with a double NKQ, the popping the element from the first and last one is always constant, right? But for the normal list, if we're removing the element from the last, it's O1. If we're removing the element from the first or anyone in the middle, it's O, right? It's ON as well, right?
Yeah.
Yeah, in general speaking, it's ON. In the middle, it's ON as well, right? Any questions so far? Do you understand what I'm saying? Actually, if it's okay, you don't understand fully, but do you understand? Or which part you don't quite understand? Maybe I can talk a little bit more, or it's okay.
It's okay.
It's okay, yeah. Okay, so tomorrow, based on this, yeah, hashing table. So tomorrow we're going to design. We're going to design the hashing table. Okay. Yeah. Okay. Do you understand? The hashing key. Look, what I said today with hashing key is to calculate a key based on arbitrary large data. It could be 0, it could be nothing, or it could be 1 million characters, or maybe 1,000 characters. So this D, the length of D is arbitrary, but the output is always fixed. Yeah, it could be 32-bit integer, or it could be 122-bit or 252-bit. You know, some cryptocurrency, cryptographic hashing functions, and they produce this 256 SHA, crypto function. So look, because this is one way, Eric, it's one way, right? You don't understand one way or two way? Do you understand one way or two way?
One way.
Do you understand? Look, if I give you a function h, Eric, look, can you tell me what is one way? If hx equals x plus 1, is this one way or two way?
One way.
Huh?
Two way.
One way, two way. Come on, think about what's one way. One way is that from left you can calculate to the right, and from the right you can calculate to the left. Is this one way or two way? Very obvious.
Two way.
Two way, of course. If I give you x equals 2, you know it's 3. If I give you the right hand side is 3, you know x is 2, right? Yeah? This is two way. But hashing function, is it one way or two way? Remember, the left is arbitrary big, 1 million characters. And the right is maybe 32-bit integer. One way. Obviously, look, 1 million characters, 32-bit. But obviously, I cannot do this reverse, right? Yeah, there's no way to reverse from 32-bit integer
Avalanche is a sudden arrival
to the million character. Am I right? Yeah. So h function is one way. Okay. So this 0 is one way. One way function. Okay. One way function. It has to be one way function. Right? Hashing table. Hashing key. And we're going to describe how to we're going to implement this hashing table. Design the hashing table tomorrow. Okay. That's it for today. Good job.
Bye 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 bye.
Bye bye. Bye bye.